I'm very excited to introduce to you Dr. Raymond Francis. Some of you guys know that I used to work at a Air and Space Museum. And so when I came here to Nevada, I was like, but come on, there's aviation and aerospace everywhere. Why don't we have it in this museum? And so I've been keeping an eye out to look for topics having to do with aviation and aerospace that also relate to Nevada. And so today we're going to have a talk about training for a Mars mission that happened in Nevada. And I'd like to introduce Dr. Raymond Francis, who is a science operations engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. He was the science team training system engineer for the Mars 2020 Rover project, leading the design and implementation of the training program and acting as field team lead. Now that the Perseverance rover has landed, he works in mission operations for the rover, guiding activity and observation planning for the science team, and operating the SuperCam laser spectrometer instrument. He also continues to operate instruments on other missions like Curiosity Rover and Aegis, and he holds a PhD in electrical and computer engineering from the University of Western Ontario, a master's in science in physics from the Royal Military College of Canada, and a bachelor's of science in mechanical engineering from the University of Ottawa. Please help me welcome Raymond Francis to the Francis Humphrey Lecture Series.
Hello, and I'm happy to be here. So shall I begin?
Well, I just want to do a sound check for everyone. Okay. I can hear him. Can everyone hear Raymond?
Yeah, can everyone out here hear me? Ask if you can hear me.
Yep.
I got a few responses in the positive, so we should be good.
Great.
Could be just a bit louder.
Okay. How about this? Is it a little better?
Is that better?
Maybe this is better. Is this loud enough?
I can hear you, mine are really well, but I can't hear the speaker quite as well. Not sure why.
Okay, let me just see what we have here. Okay, and is that any better? Can anyone else confirm you can hear me all right?
It is for me.
Okay, great.
Yes, and I can hear it.
Okay.
I hear fine.
Fine for me also.
Okay, that's enough people that says it's fine. That's probably fine. Okay. Well, I do have a slideshow, so let me see if I can share that. And we'll try this. And so the first question, do you see some slides?
Yes.
Yes.
Okay.
Yes.
And do we still see the slides? Yeah, okay. All right, great. Okay, so as you heard, I work at the Jet Propulsion Lab in Pasadena, and I'm working especially with the Mars 2020 project, the one that operates the Perseverance rover, which landed a few months ago on Mars in a place called Jezero Crater. And it was a long road to get there. I'll talk a bit about the mission and how it was developed, but that road took us through part of Nevada near Walker Lake, sort of in the western side of the state, as part of an exercise to train the science team that would operate the rover. We wanted them to be ready to go to use a rover to explore Mars rather than learn as they went after we arrived on Mars. We wanted them to be ready and trained up before the rover landed. And so we did some of our training in Nevada near Walker Lake, and I'll talk a little bit about how and why we did that. But first, I'm going to introduce the mission. So this is an image, artist's rendering, and we'll show you some real photos later, of the Perseverance rover. this vehicle, for scale here, it weighs about a metric ton. It's the size of a sort of small compact SUV. It's a big vehicle, especially one to send to Mars. And it has to be that big to carry all of the science equipment that we had to pack into this in order to do this ambitious mission that I'll describe in a bit. And a vehicle of this scale is a complex system to operate. We have hundreds of people working in operations for this vehicle on a regular basis. And so it's a big, complicated project. And one of the pieces of it is training people to use a vehicle like this and its instrumentation to do science. And there's a lot of science you can do with a vehicle like this and with these instrumentation, but you can kind of boil it down to 4 main goals that we have. And they are very ambitious goals that are all centered around the theme of life. We want to understand the possibility of life on Mars. In particular, we're looking at ancient microbial life. It's still thought to be possible that in the distant past on Mars, there may well have been a time when life arose and lived and thrived on the surface of that planet. And we want to understand how likely that was and actually seek out signs of such past life. We're already convinced that there are places that were habitable. The question is, were they inhabited? To chase that down, we're going to be doing geology and looking for the kinds of environments where that life might have lived, but also where the signs would have been preserved. And looking for those signs means we're doing something called astrobiology, seeking life outside the Earth. Now, despite all the instrumentation that we carry with this rover, it's actually not possible for us to really get to the bottom of that question simply with what we call in situ measurements, with measurements that we make with instruments that we can send to that location. If we really want to convince ourselves and convince the world that we have found signs of ancient life on Mars, we're going to need to bring all of the best equipment that we have here on Earth. All of the laboratories on Earth will need to be brought to bear on these materials that have putative samples, signs of ancient life. And so that means that we're going to be collecting samples to send back to Earth. And this is the first time that that's ever been attempted. So that in itself is an ambitious goal. Finally, we're also doing some things on this mission which are looking to the future and the possibilities of human life on Mars in the years to come, particularly if we send astronauts there to expand our exploration and what environments they'll face and they'll have to understand. So we're doing some things for the future life as well. This mission, as I mentioned earlier, has been in the works for years. In fact, not long after the Curiosity Rover landed successfully in 2012, NASA announced a follow-on mission using a lot of the lessons and a lot of the technologies that were developed for Curiosity. And so since early 2013, we've been in the works developing this mission and its instruments and planning out what we would do. It took us until almost the end of 2018 to actually select the best site to send this rover to. A place called Jezero Crater was selected of all the places on Mars after years of deliberation among the world's Mars science community and astrobiology community about what would be the ideal place to go study. And in parallel, we were designing and building the rover and the mission system and all the things that support it. The mission was launched in July of 2020, cruised to Mars over several months, and landed in February of 2021. Always a risky business trying to get down through the atmosphere of Mars and land safely on the surface. That was successful. And so now we're in what's called the surface operations phase, where we operate on the surface of Mars and we're exploring and making science measurements, and all the plans that we made are rolling out. So some of you may be familiar with the Curiosity Rover. We've been sending back pictures from that vehicle since it landed in 2012. This new vehicle looks pretty similar. The Perseverance rover is based on the Curiosity design, but there are some key differences, and it's worth noting we upgraded some of the science instrumentation, especially those that are out on the end of the robotic arm here. And these, because they're larger and heavier, meant that we had to upgrade the arm. And so we have a larger robotic arm. And that made the vehicle heavier. We had to stiffen it and strengthen it with this aft crossbeam, which is something that you will only see on Perseverance, not on Curiosity. Also, sticking out of the front of the rover here, you see this kind of circular feature. This is part of the sample caching system that we call the bit carousel. And it basically is where drill bits are stored and swapped and interchanged. And this is because we have the sample caching system on Perseverance, which we didn't have on Curiosity. Those with keen eyes will also notice that the wheels are a little bit different. The zigzag cleat pattern on the old Curiosity wheels has been replaced with something that's very, very gentle curves on here. And this is a redesign of the wheels that we did based on the experience on Curiosity. And we've also upgraded most of the science instrumentation, including the cameras. There are many, many cameras to do different things on this vehicle. Just to give you an idea of scale here, I said some of those instruments are out on the robotic arm, and here is how big the vehicle is. This is the real vehicle in the assembly facility at JPL. And these people are all dressed up to protect the rover from static discharge and little bits of skin flakes and hair that they might drop, because we want to keep this thing perfectly clean to protect the electronics, but also to protect any samples that it takes. This is just putting the arm through some tests here, but it's a good example of just the many, many things you have to do when you're building something this specialized to send to Mars. And it gives us an idea of the scale and the size of the vehicle. Now here's a real photo from Mars taken by a camera on the end of the robotic arm, looking at what we call the remote sensing mast. And some of the instruments are held up here. I mentioned cameras. So we have these little circular features, left and right are the navigation cameras. We use these to see what's in front of us and where to drive, but also to build a stereo view of the world around the rover in which to see the objects, the rocks and things that are around us and point the other instruments at it or place down the robotic arm. And some of those other instruments include the science cameras here, Mastcam Z, they call it. These are stereo color zoomable cameras for taking images for science purposes. But we also have something called SuperCam. And this is up here looking through this window, which is actually, you're seeing a reflection here. This is a mirror because this is a reflecting telescope. SuperCam is a very complex instrument with a number of different sensing modes. But chiefly what it does is it focuses a powerful laser through that telescope on rock targets up to 7 meters away from the rover. And it can work in a couple of different modes. One of them is called laser-induced breakdown spectroscopy. Here, that laser is used to focus on the surface and deliver something like a megawatt per square millimeter. This is a lot of power. And it's enough actually to vaporize the surface, turn the rock surface into a plasma. And that glowing plasma is then imaged through that same telescope with a spectrometer inside the rover. And the wavelengths of light that plasma emits tells us exactly which chemical elements the rock is made of. Now, this is how we tell the chemistry of the rocks around us, is with this powerful laser. We have another sensing mode called Raman Spectroscopy, where at a different laser wavelength, we just excite the molecules and get them shaking. And that tells us about their crystal structure instead of destroying them and getting the elemental chemistry. It also has a context camera that we call the remote micro imager, but it can take pictures like this. And you can see in this sort of very narrow field image of a real rock on Mars taken by the SuperCam a couple months ago. You can see the surface of the rock in great detail, but you can also see a row of spots that were burned by the laser. The last one right in the middle of the image. This is how we typically do it. Take an image, make a few spots, take a final image. And this tells us what it is that we measured. So this is the kind of instrumentation that new members of the science team have to learn to use. We don't usually work with remote laser spectrometers on Earth because firing powerful lasers around like this is dangerous, but there's no one else around on Mars, so it's safe to do there. Other instruments, for example, on the robotic arm, we have a pair of instruments called Sherlock and Pixel. Sherlock has a Raman spectrometer similar to SuperCam and also does some sort of cathodoluminescence, where it excites the molecules and the atoms in the rock. And it works in a bunch of different modes, but it gets us the chemical composition again. And Pixel is sort of an X-ray instrument. It's an X-ray spectrometer working at a very different wavelength. And so there's different elements and different compositional aspects of the rock that it's sensitive to. These are on very, very fine scales, though. So here's a test that we did on Earth with test versions of Sherlock and Pixel, looking at this rock here with preserved bacterial mat layers that's from Australia. And zooming way in on this rock, we picked a place. The square field of view is for Sherlock and the overlapping rectangle is Pixel. And this is only a few millimeters across. This is a very small, fractions of an inch size area, which means we can get unprecedented resolution, which you need if you're looking for tiny, tiny things that might be left behind by ancient bacteria. But it also means that you can't put these instruments everywhere. You have to decide where to put these down. We can't do an exhaustive survey with something that has such a tiny field of view. So the wide field cameras are used to choose where to go, and then SuperCam can be used to do surveys of the composition of the rocks, and then we pick which one or two in an area we want to put down Pixel and Sherlock. And this is the kind of strategy you might use. And the kind of strategy you have to learn if you're going to be using a rover to explore a place on Mars. We also have a ground penetrating radar, and this is a much larger picture kind of instrument. It measures the structures underneath the rover and helps us connect the subsurface structure below all the sand and gravel-y type dirt that you would see, regolith we call it on Mars, with the hills and structures and other things that we observe around us, and helps build a 3D picture of what's going on. We also look at the atmosphere, not just the rocks. We have a weather station, which is useful for some of our own operations, but also as a record of the current climate on Mars, building up a record that goes back decades now of Mars surface missions. And this will be useful if we send astronauts into the coming years, because you need to know what kind of environment you're gonna have to deal with when you're working outside on Mars in spacesuits. So we measure things like temperature and pressure, but also how much dust is in the atmosphere. That turns out to be a major aspect of the weather. Here on Earth, water vapor controls almost everything, but dust is a big factor on Mars. And I mentioned the sample caching system as well. This is something that really drives what we're doing, and it's a new capability that we didn't have before. So I mentioned that we're going to a place called Jezero Crater, and this was selected because it is quite possibly the oldest lake on Mars. Now it's a dry lake bed now. There's no more surface water, but at one time there was a lake here, and we can see the evidence of that in the shape and structure of the landforms that are there now. Some of them absolutely look like shorelines or lake bed sediments. Also in the chemistry, and this is an image taken from orbit, which is colored based on the different minerals that you see. And many of these are minerals that you can detect from orbit. The signal is that strong. Many of these are minerals which only form underwater. The chemistry of these demands that they form in a wet environment. So there had to have been water in this place. But even more, what you're seeing here, there's a row of hills along the left side of the image. And this is the crater rim of Jezero Crater. And there's a break in the crater rim here. And through that, there's a river channel. It looks just like a river channel. And in fact, at the end of that is a large delta structure, the kind of delta you would find at the end of rivers in the Mississippi or the Nile, rivers that carry sediment and deposit them into a standing body of water. You can only do that when there's a standing body of water, but also deltas take a long time to build. These don't happen overnight. A catastrophic flood will not produce a structured delta like this. And so you need a long period of time. And that means that the lake had to have been there for a long period of time. So here we have an ancient lake, and an ancient lake which is stable on long periods. That's the kind of place that you would look for life on ancient Earth. And it's in fact estimated that this was happening in Jezero Crater about 3.5 billion years ago, maybe 3.6 billion. And that's around the same time that life was arising on Earth. That rock from Australia is around the same age, and it's a preserved record of bacterial mats. These are structures produced by bacteria, some of the earliest sort of preserved ancient signs of life on Earth. So if Mars had surface water lakes and Earth had surface water lakes at about the same temperature, at about the same time, in the same time in their planetary history, and life was arising on Earth, it seems plausible that it might have been arising in similar environments on Mars. And so this is why Jezero Crater is such a promising place. And it's the kind of place that we have to learn to explore. So I do have a little video here which shows Jezero Crater in some more detail. Here's the crater itself, and you can see on the left where that river channel comes in. This blue is the landing ellipse here. It's the area we expected to land. There's some uncertainty there. And as we zoom in, you can see the delta again. And you'll see this crater here in the middle is about 1 kilometer across, so sort of 2/3 of a mile. And you can see the structure of this, and we're going to zoom in a little closer. And you can see just how tall the cliffs at the front of the delta are. There is a lot of sediment here. This took a long time to build. So we actually ended up landing very close to this position here, and this is a sort of notional traverse that we might take in the future. But you can see, and it'll highlight in a moment, just where the river channel comes in and breaks the crater rim and the delta itself. And this broad floor of the crater as well will be an area of interest here as we drive towards the delta.
I'm watching TV. Yeah.
Very good. And so just to fly over the delta here, you can see there's a lot of structure and topography. It's gonna give the team a lot of puzzles to solve. These are modern sand dunes that we're flying over now, but over here we have ancient shorelines. You can see all the little ridges of ancient beaches that waves used to wash up on in the distant past. After we explore all that, there's a good chance that we're going to come out towards the end here, take a look at the river channel, and then explore areas outside the crater. And so you'll see that we've extended our notional traverse into the country around where the crater is. This is sort of our notional plan, and we're still refining that now that we're on the surface and we know actually where we've really landed. But this is what Jezero Crater looks like. So that's the mission. This is, we have a big complicated vehicle, we have a lot of science goals, and we have a place to explore on Mars. And this gives us some challenges. As I say, the mission is very complex. There's a lot of moving parts here, both literally and figuratively. And we also, because we have all of those different kinds of science instrumentation and many different kinds of scientific analyses to do here, we have a very diverse science team with all kinds of different backgrounds and varying levels of experience. Some of them have been working on the other rover missions for years, which means they have to learn how to work on this different rover mission. But others are completely new and have not worked on rovers before. The ground penetrating radar team, for example, they're from Norway, and that's the first time that country's participated in one of these missions. So most of the people on that team don't have any experience with this kind of thing. So we have to get them up to speed. And as I say, Jezero Crater, there's a lot of diverse terrain. We have lakes and deltas and lake bed sediments and lakeshore sediments all inside an impact crater with its own geology and a surrounding regional geology, which is again different. So there are a lot of geological puzzles to solve there, and the mission will not last forever. We only have a prime mission of about 2 Earth years, and hopefully some extension beyond if the rover keeps working, to take these samples. And we want the samples to not just be random holes on Mars, but the result of real geological exploration and analysis. And we want to choose where to take samples correctly. What are the best places to sample? We want to be able to determine that. And we're going to be doing this in a place that we haven't explored before. No one has ever sent a mission to Jezero Crater. And we will therefore only have the data sent back from the rover's instruments to understand this place. We have to do all of our learning and strategizing and exploring based on what we take in data ourselves day to day with this mission. So every day we have to ask ourselves, what are our questions that are still open and which data should we collect to answer those questions? And tomorrow, where are we going to be and which data will we want to have to do what we need to do tomorrow? Always planning for today and setting ourselves up for the next cycle, as we call it, the next command cycle. These are the things you have to prepare for, and these are the things you have to learn if you're going to effectively use a rover and a set of instruments like this to explore a place on Mars. And to get ready for that, we prepared a program that we called the ROAST, the Rover Operations Activities for Science Team Training. And this was a series of highly realistic mission operations simulations, which were done before the rover even launched, during the development process of the rover. While the science team was finishing up designing and preparing their instruments, they were also learning how to take part in mission operations. And in these simulations, we used the same operations process and the same timeline, the same kind of organization of roles and process as we would on the real mission. And we also used all of the same operations softwares, or at least the prototype versions of those tools. There's special software you use to plan out where to drive the rover and where to point instruments and things and what to do each day with the rover. And so we brought that software in front of the eyes of the science team and said, use this to plan what you're going to do. We also wanted them to have real geological puzzles to solve that were relevant to what they were going to have to do on Mars. So we found what we call a Mars analog field site. In fact, 3 of them. And these were places that had realistic geology, realistic exploration scenarios that gave them meaningful geological questions to answer. And we also, especially for the last one, wanted it to be something that was not known to the science team. Not a place that they had all been to before or a place that was well known in the geological literature. We wanted something that was new to them, like Jezero Crater would be. We also wanted this to be an exercise where they got what they did. They got what they asked for. If they requested science data, they would have it the next day the same way they requested it. And if that meant that they had made a mistake in requesting something and they didn't get what they needed, but they got what they asked for, that's how rovers work. If you give it a command, it's going to do what you say, and you'll get what you asked for, not what you need. So teaching them to ask for the right things meant giving responsive science data. And so this wasn't a canned exercise where we took a bunch of pictures and then fed them data from a place. We actually had a field team collecting data in response to what they asked for in mission control and sending it to them shortly afterwards. We also wanted representative data, which is to say that it was similar or pretty close to what the real rover would send them, as close as practical, so that they would be making decisions based on more or less the same kinds of information they would have when we get to Mars. And we also did the cycling of commanding the same way we do on Mars. So they would plan out a set of activities and deliver it as if it was being uplinked to Mars. And then the field team would respond to that. And then they would come in the next day to mission control and get the results, just as we do on Mars. So if we're going to run an exercise like that, I say we want a Mars analog field site. Well, there are a bunch of requirements on that. First of all, we wanted, for the third and final, the biggest of these simulations, we wanted something that was very similar to Jezero Crater. We wanted sedimentary rocks above all. And if possible, we wanted lake bed sediments or lake margin sediments, sort of shorelines and lake beds, because that's the kinds of things we're going to see in Jezero. And those are also places where we expect there's a high likelihood of preservation of organics and of signs of life. But it also has to be a place that is plausibly rover accessible. There are lots of interesting geological field sites on Earth that you can get around in a pair of boots, but that a robot could not drive around. And we want them to make decisions about where to go, which are similar to the ones they make on Mars, which means we need them to be deciding that they can go here, but they can't go there because the rover can't drive there. So we want a place that's realistic in its rover accessibility, and have rock outcrops that are scientifically interesting, but also that the rover could approach. We also wanted a place that looked like Mars. It didn't look like it was full of anthropogenic features created by humans, because there aren't those on Mars. And so we don't want human-made objects. We don't want a lot of buildings. We don't want any other features that would distract from the simulation or would reveal the scale. When you look at a rock in a picture from Mars, it could be hard intuitively to guess how big that is. Rocks can be any size. But if there's footprints or if there's a fence post next to that rock, it can be immediately apparent how big that rock is. And we didn't want things that would break that scale question down too easily. Other things that we don't have on Mars is vegetation, so we wanted to minimize that. And we wanted the landforms to be as natural as possible. So, you know, we wanted to be in a nice natural geological environment, not with constructed berms or earthworks. And we also wanted as few visitors as possible during the exercise. You know, if you go to some popular national park, you're going to have people hiking through, and that will get in the way. And we don't want people like that to get in the images. So we wanted a place that wasn't very busy. That's on the science side. Now, just on the practical logistics side, we want a place that has reliable weather. We don't want it to be raining or snowing in the middle of the exercise, because that will get in the way of doing our job. And also Mars doesn't have rain and snow. And extreme wind makes things really difficult for some of the work we had to do. From a safety perspective, you know, we're going to have people running all over with instrumentation. We want to make sure that the hazards are minimal and manageable. There are emergency services available. We also need to be able to get there. There's all kinds of places in the far reaches of, for example, the Canadian Arctic that might have been interesting, but it's just really difficult to get all the way up there. And we have heavy and sensitive equipment that we not only need to get to the field site, but that we have to be able to place right up near the rocks to make measurements. And just from a practical perspective, we need somewhere where we can get the internet, or at least near where we can get the internet, so that we can send this data back to mission control. And we want telephone service, so we can be having the field team coordinate directly with the operations people at JPL. And we need electrical service, so we can charge up the equipment, and things like food and fuel, emergency supplies, stuff like that. Oh, we need a hardware store, because if we need some screws on the camera system, this kind of thing. So we did find a place that met all of those requirements, just outside of Hawthorne, Nevada. And this is practical in that it's about a day's drive from Pasadena, so you can deploy a team easily. And we made several trips to Hawthorne to scout it out and eventually to do the exercise. It meets our geological desires. It's in the margins of a lake. There's this Walker Lake here, which has been shrinking over the past several decades. And so we're on the outermost sort of former shorelines and even former lakebed from thousands of years ago. And so it is exactly what we wanted for in that sense. And the rocks around here are sedimentary rocks formed in lacustrine, as we say, environments. It's also a sparsely populated area. There's not a lot of traffic in this part of the desert. The town itself is busy like a town, but out here in the desert away from the town, there's not a lot of people going by. In fact, this valley is mostly filled with a large military base, and fortunately one that doesn't have many visible buildings. And so the land we were on is actually controlled by the Department of Defense, so they don't get a lot of visitors there. And this place is a very interesting geological analog, but it's not been studied a great deal and published about very much. And so the Mars geological community is by and large not that familiar with it, which is exactly what we wanted. It's a place that is not well known to our Mars scientists. And for all the logistical needs, the town of Hawthorne is right there, and it provides everything we need. So that's why this place got picked, and it turned out to be an excellent location. This is what that place looks like on the ground. We have sort of natural outcrops, a little bit of vegetation in some places, but for the most part, very sparsely vegetated. And we have nice rock outcrops, flat areas that rovers can drive around, outcrops that can be approached, loose rocks here and there that are also worth scientific study. This is the kind of place that we're at. So this played really well into our exercise design. And we gave the science team a scenario that would fit this site. So here we have a sort of orbital image here. It's actually air photos, but we're pretending that it's taken by a Mars orbiting satellite. And we've told them that we're doing an exploration campaign in this sort of orange region, and the blue path is where the rover has been so far. We told them, look, the rover has already visited 3 locations near the shore of ancient Jezero Lake and made some initial surveys. And here are those 3 locations seen up close here. This rock outcrop, somewhere up on the hill here, where there's, again, some outcrop. And then on the other side, at number 3, a different outcrop. And they all look different. They're related to each other because they're different layers at different elevations here. And so they form together a suite of geological units that make some kind of history and that's recorded here. So the question is, with this initial data, science team, how will you explore this place? And which 2, we only have time to explore 2 of them in detail, which 2 do you choose? And then we're going to run an exercise with daily planning as if it was the real rover on Mars to explore these. And you have to choose day by day how you're going to use limited time, limited resources, limited data volume, bandwidth to send back from Mars to study these places. And then at the end of the exercise, choose only one of these to sample. And this was meant to make them do some of the same kinds of decision making that they will on Mars. They're going to have to, there'll be many, many interesting places, but they won't be able to explore them all. And in the end, only a small number of the total places explored will be sampled. So we forced them to make those kinds of choices. So here's the timeline. This is in the winter of 2020. So in January, there was all kinds of preparatory training for the team. This is how the exercise is going to work. This is how you do rover operations. This is how you use the software tools. This is a reminder of what the instruments are like. And then in the first couple of weeks of February, we gave them the initial data from those 3 sites and had them do, through structured discussions, a review of that data and debates and deliberation about what it meant, and make their choices. And then they picked where they would go first and which 2 places they would explore. And then from February 19th to 27th, we had this operations planning exercise. And the way we scheduled it is that instead of working every day to give ourselves some margin and some wiggle room in the schedule, and also just to accommodate the fact that these people have other work they have to do to prepare the mission, we actually had them work every second day, more or less, where they would spend a day planning what to do with the rover for a day on Mars. And then on the next calendar day, we would send the field team out to collect the data. That data would be processed and sent back to JPL and to be ready in time for the next uplink cycle. They'd use that information to plan the next day's activities. And so we sort of worked every second day, where on the real Mars, we work every day. Or at least this is what we told the science team we were doing. In fact, we were able to get a jump on this data collection, and most of the data was usually collected the same day by some kind of careful scheduling. But nonetheless, we were always taking exactly the data they asked for. And so what we were using this day in between as margin, which we sometimes needed because of weather or equipment issues or whatever. But this strategy worked out really well for us, sort of planning every second day. And after they had gone through this and sort of planned out what was basically a week's operations on Mars, we then gave them sort of some final data to add to this. And they had, in the beginning of March, a final set of deliberations and discussions where they interpreted the data, made decisions about what they had seen, and chose where their final sampling site would be. And that was sort of end to end, a kind of version of how to do a geological campaign on Mars, made them make the right kind of decisions, and by and large did what it was supposed to do. So what they saw, what the science team saw during this exercise was this kind of thing. They would be working in mission control with software tools like this one here, which shows you a 3D model of the environment. And it places the rover in that scene to give you a sense of scale and to understand where the rover is relative to the rocks. And they can move this 3D scene around and explore the environment. And they can also call up images like this one. This is a very close-up image meant to represent the RMI, the remote microimager of SuperCam, but also images from other cameras on the rover. Looking at, this is just an example of an image of a rock that was taken. We also gave them all kinds of spectrometer data, matching more or less all the different spectrometers we have on the rover, the Sherlock, Pixel, SuperCam type instruments. And we were giving them weather data too, as if it had come from the weather station on the rover. And so they had all of this data to work through and to make decisions and then plan where to go next. And you can see places that they're selecting, oh, maybe we'll make an observation here, and here's a target that they've named that they're planning to make measurements on. So this is how it looked in mission control. And as far as they was concerned, they were on Mars, and the only thing that was different was the blue sky, which we couldn't change. But for the field team, things looked very different. There was no rover. In fact, we had a team out there with all kinds of instruments doing everything it took to simulate that data and make it look like it was coming from Mars. And so here we have an infrared spectrometer on a backpack and a little computer to read the data. And this team is making measurements of the rock surface in a place where the science team said that they would point the SuperCam. Well, we don't have a SuperCam, but we do have an infrared spectrometer, which replicates part of SuperCam. And then we also have this laser-induced breakdown spectrometer, which replicates another part of SuperCam. And here's, again, one of my colleagues making a measurement as if it was coming from SuperCam. We have a ground penetrating radar, and this here is a little cart that carries a ground penetrating radar. And this engineer is pushing it along on exactly the path they said they would drive the rover on, and making measurements very similar to what the RIMFAX GPR on Mars 2020 would make. Here, this is me simulating an image with a digital handheld camera mounted on a little tripod, specifically to simulate an image taken by the rover's robotic arm. And here, this is for the remote sensing mast with the stereo science cameras, the Mastcam Z. This is a Mastcam Z simulator, which was lent to us by the Mastcam Z team at Cornell University. And here they are out in the field taking images in exactly the same camera system that you would use on Mars. All the same filters and the same resolution and zoom settings. And they even sent us a graduate student to operate it for us. And then when they decided to sample and make initial measurements where they would grind the surface of the rock to reveal what's inside before deciding whether to sample, here we have a handheld drill with a drill bit that matches the one on the rover. And we're grinding away the surface of this rock to make measurements. So this is how it looks in the field. Nothing like it does on Mars. But we had a field team who did a pretty good job of making a convincing simulation. And the field site was very useful for that. So the exercise was pretty successful, and the science team reviewed it very highly in terms of preparing them for the surface mission. And as I say, it wrapped up in March of 2020. And that's basically right after that, we got into the final prep for launch and the final preparations for the surface mission. The launch happened in, this is from Cape Canaveral in July 30th of 2020. This is the launch of the rover, and it's followed by some 7 months, hundreds of millions of miles, hundreds of millions of kilometers, with the rover trapped in this little capsule here, protected against the space environment, but even more against the atmosphere of Mars when it arrives, powered by this solar array out here. This long cruise ends when it gets to Mars on February 18th of 2021. Something like 120 kilometers above the surface, we have what's called entry interface, where it begins to feel the atmosphere. And you may have seen animations of the Curiosity landing or even of the 2020 landing system. It's a big, complicated, multi-step process where the the cruise stage separates and you're just left with the capsule. It enters the atmosphere. The heat shield slows things down, protects the vehicle. Eventually, it gets into thick enough atmosphere that it can actually steer itself a little bit like a lifting body to try and center itself more closely on the target. Then this supersonic parachute slows it down. Heat shield is dropped away, and it knew on 2020 what we didn't have on Curiosity mission. It actually has some terrain relative navigation where it's figuring out from a map on board where it is relative to the Jezero Delta and deciding how to steer to get to exactly where it wants to be, right close to the center of the landing ellipse. Once it gets as slow as the parachute can get it, it separates from the parachute and comes down on rockets, what we call powered descent. And then finally, to keep those rockets from blasting rocks and sand at the rover, actually lowers the rover down on cables before, once the rover's on the ground, cutting those cables and flying away. So there are animations of this out there, but I'm going to give you a view from the rover during this descent. So this actually happened. Here's a view looking from the camera that does that terrain relative navigation. You saw the heat shield drop away there. There's Jezero Delta, like we saw before. And there's the crater floor. And we touched down right about here, right about there. And it's all moving around here, but that's what happens when you are hanging on the parachute a little bit. Now we're coming down on rockets, and pretty quickly we get to the surface. There's a rover wheel and a bunch of flying sand. And we'll let that play through again briefly. So these are real images. These are taken by the descent camera. And that's the view the rover has as it's coming down. And we didn't get these in real time. We were getting telemetry telling us that these events were happening, but we didn't get a live view of it. But just shortly after this happened, just shortly after the touchdown, and we got the telemetry saying it was successful, we did get this image. And this is sort of the first real big color image that we got back in mission control. And I'll tell you that when we saw this, we were very excited because this is the rover hanging on the cables from the descent stage, just a few feet above the surface, ready to touch down. And everything we want to see is here. We're on flat ground. The wheels have deployed. The cables and everything are looking as expected. Everything is in the right place. Nothing is bent. There's no damage to the rover. And you can actually see we're just about to touch down because the rockets are actually impinging on the surface here and blowing away streamers of dust and sand. This is just before touchdown. So this is the image that tells us everything looks great. And it's, with the Curiosity mission, when we had a very exciting landing, but we kind of had to imagine it all because we didn't have cameras during the descent. This is the first time we actually got to see it happening. And so we were, the team was thrilled to see this. But the science team was perhaps even more thrilled once we started to get pictures like this. This is an actual mosaic of images at the landing site. And you can see that place that we saw from above where the rockets had blown away sand. Well, this is that cleared spot on the ground from the rockets. But further out in the distance, you can see the landscape of Mars. This row of hills is the rim of Jezero Crater. And remember that break in the rim where the river valley comes in, that's right here. A little bit closer, you can actually see this ridge here, and especially along here. This is the front of the delta. Now it's hard to see in this image, but we can zoom in. So I'll zoom in on this little area here. This is how that looks to SuperCam in the remote micro imager. This is 5 RMI images that have been mosaic together 2.2 kilometers away, like a mile and a half or so away, through the telescopic imager of SuperCam. And you can see that indeed there are, not only is the delta here and forming a kind of a hill, a cliff, but there's structure here. There's layers in the rock, and some of them seem to be at angles and things. So this is promising because it tells us, oh yeah, we will probably be able to study the structure of this thing and understand how it formed. And also tells us that the SuperCam instrument is working. But not just for taking pictures, we can also take spectra. This is the first spectrum we took on a rock that we called Mars. It's the Navajo word for Mars. And we're already getting composition on this rock, but also on plenty of other rocks. One of the things that we found is that there's a great diversity of rocks in the surface here, not unexpected. We are, after all, in a lake bed near a delta. There's been, sediment flowing into this place for a long time, but the crater floor has its own geology, and so does the crater more generally, and the environment around. Plus, meteorites fall out of the sky sometimes, so these rocks can be kind of from anywhere. So you kind of expected a diversity of materials here. And it gives the science team a whole lot to work on. Now, not just the rocks are interesting. We also have here a dust devil in the background. The atmosphere is quite active here, and we've seen several of these now. You can just barely see this dust devil moving from left to right. And this was not a set of images that were taken to catch dust devils. As you can see in the middle, the robotic arm is twisting around there. This was actually a set of images that were taken as part of checking out the instruments on the arm, just inspecting them with the rover's navigation cameras. But there in the background, Mars is giving us little gifts in the form of dust devils. And the atmospheric science team is very excited. They're also excited about the fact that we now have regular weather observations here since a couple of months now. The Meta weather station, Mars Environment and Dust Analyzer, includes a wind sensor, which you can see deploying successfully there on the left. It was folded up to protect it from any flying debris during landing. And on the right, we have this all-sky imager, sort of a fisheye lens looking up. And that dark ring inside the SkyCam imager here is actually what we call a neutral density filter. And it's meant to be sort of a solar filter. This is like kind of the sunglasses for the camera. Very thick solar filter that blocks out most, but not all of the sun's light in a very calibrated way. And if you look very carefully, you may see there's one little bright pixel right here where the sun actually is hidden by the neutral density filter. And that allows them to actually measure how much sunlight is coming in, which depends on how much dust is coming. And so this is one way of measuring how dusty the atmosphere is each day, is just waiting for the sun to cross that path and get a calibrated measurement of sunlight amount. So things are working well with the rover. And here's a picture, actually a collection of images stitched together, taken by the arm-mounted Watson camera, partner to Sherlock, you might note. And here's the rover, and the rover's looking off in the distance at its little partner, the helicopter. And you may have heard that we actually, as part of a sort of technology experiment, carried with us this little helicopter, the first aircraft ever to fly on Mars, and the first powered aircraft to operate on any planet other than the Earth. And so here you can see the tracks of the rover where it drove over, dropped the helicopter, and carried on, and another pair of tracks from earlier when we were scouting out the area. This is the first time we've been able to take a sort of team photo like this on Mars. Looking up closer, this is what the helicopter looks like. And this is a little video of when they released the blades. They had been locked for launch. And when there's so little friction in these that just releasing the launch lock actually causes them to spin around a couple times. The helicopter has been working very well. And this is this thing that's gotten a lot of attention here. This is an image taken by a down-looking camera on the helicopter at the ground. There's those same tracks that I showed you in the previous image, and what you're seeing in the middle is the shadow of the helicopter. This is taken near solar noon, so the sun's almost directly above the helicopter. And that's the helicopter imaging its own shadow. This camera is used for navigation. The helicopter knows how far it's flown by tracking how the rocks are moving past it in the images. But the rover also has cameras, and you can see the helicopter in it. This is an image of the helicopter, and it's actually a video of the very first flight that we did on April 19th. And you'll see the helicopter sort of spin up a few seconds into the video here. There's the blades preparing. This little tiny helicopter, which only weighs a couple of pounds, the blades spinning at something like 2,600 RPM, which is very fast, and there it goes. Lifts itself off, climbs to about 10 feet altitude, and hovers there and rotates deliberately, about 95 degrees of rotation, just to show controlled maneuvering. This is the simple flight, the very first flight. We've got much more ambitious since. but this is the very first flight on another planet. So among the early highlights, and there will be more results from the science mission as we continue our exploration, and we're just sort of wrapping up commissioning the instruments and doing the helicopter tests, and the science mission is just beginning. But they're already applying the lessons they learned in Nevada and on the ROSE program, and there's a lot more to come from this mission yet over the next sort of 2 years of the prime mission, and hopefully extended mission beyond that. And you can follow all of that online. We post all those images on the project's website as soon as they come down, and we have news that's posted regularly, so you can continue to follow the excitement as we explore Jezero Crater. So that's the end of my slides, and that's what I have to say. And I think we have time to take questions, so I'm happy to do that.
Oh, thank you very much.
Mhm.
We had a couple of questions while you were talking. So
Okay.
I'm gonna, repeat those. Let's see if I'm deaf, whatever. Okay.
Mhm.
It says, is there a plan to examine the crater on top of the delta? Seems like it could be an interesting look into a cross section of the delta.
Yeah, that's a very good thought. And I'll just run back to the map here that we have. Yeah, this might well be an interesting place. You have to be careful driving into a place like that to make sure you don't get stuck. You got to be able to come back out. But even just the rim of it would be very interesting. And so, yeah, it's a place that we've thought about going to. The science team is still deciding on its strategic route, so we may or may not actually go there. But even if we don't enter it, you can imagine that imaging it would be very interesting, just to see from a distance what is exposed in the delta. We have another way of looking at the cross section of the delta, though, which is to look from the side at these cliffs, and that probably goes to a greater depth. Actually, this is a fairly shallow crater, so we have several different ways of getting at that.
And then we have another question that says, how is all of the sensitive equipment protected from dust?
Yeah, so a lot of it is enclosed. The spectrometers, for example, of SuperCam are hidden inside the body of the rover. Where's a good way to show that? So yeah, a lot of things are kept inside the body of the rover. The ground penetrating radar, it doesn't really worry about dust, so that's okay. And it hangs out on the back of the rover. Some things on the surface, like I don't really have a good picture of it, but the calibration targets for some of the instruments or the parts of the weather station actually have little magnets beside them, because the dust is slightly magnetic. And so as the dust is falling towards some sensitive part of the instrument, the magnet will actually pull it away and catch the dust. And so some of these things you'll see as the rover gets older, you'll see areas where there's sort of a ring of dust around something, and that's from that. And then yeah, most other things are well enclosed like that, but some of them just have to be built to be exposed, and you just sort of have to live with that. You can see already the wheels are getting pretty dusty, but that's okay.
So I have another question about the power systems for the rover. Is it solar or what?
It is not solar. If you look here, you don't see any solar panels at all, but this large structure on the back, you can see there's a kind of a cylinder with fins sticking out of it here. And what this is a radioisotope thermoelectric generator, an RTG. And what this does is it has, in the center of it, it has an arrangement of sort of a ceramic brick of plutonium oxide. And it's a particular isotope of plutonium that, when it decays, basically just generates particles that are reabsorbed by the brick and then emit heat. So it's basically just a brick that gets hot because it's a little bit radioactive. So that's the thermal part. And then, as it turns out, there's something called the thermoelectric principle, where if you take a conductor, a bimetallic conductor, and you put one end of it on something warm and the other end of it on something cold, it will generate a voltage. And if you put a whole bunch of them in parallel, you can add up that little bit of power and create a meaningful amount of power to do something. And so what we've done is we've got a bunch of these thermoelectric elements that the hot side is on the hot plutonium brick, so to speak, and the cold side is on the cold atmosphere of Mars. And that's the radioisotope thermoelectric generator. And so all the rover's power comes from that. A lot of waste heat comes off that thing too. And we have a sort of thermal cooling, a thermal, not really for cooling, it's for warming loop that runs through, but it's kind of like the lines in a refrigerator or a heat exchanger that use that waste heat just to keep the rover warm, because electronics don't like to be cold, neither do motors.
So I have a follow-up to that.
Mhm.
You were saying there's a primary time of the mission and maybe extra. What determines that?
Yeah, so the prime mission, which is sort of what NASA has chartered us to do, is 1 Mars year, which is just a little under 2 Earth years. And the extended missions are, NASA will authorize extended missions if the spacecraft and its instrumentation are still in good shape and if there's still good science to do. And from all that you've seen here with the equipment we have and the exciting field site we have at Jezero Crater, it seems likely that there will always be good science to do here. The question is whether the rover will be in good shape. And these Mars rovers have a pretty good track record of outlasting their warranties. The very first one was built to do a 30-day mission and lasted about 90 days. The next ones were built for 90 days and lasted 6 and 15 years. And the Curiosity rover is now 9 years into its 2-year mission. So this isn't a promise that Mars 2020, the Perseverance, will go on that long, but we're hopeful that we will get a few years past the warranty on this one.
So that's interesting. So the reason I thought that was a follow-up is because I thought that the plutonium or the radiation would run out. But you're saying even Curiosity is still going on their nuclear power.
Yeah, and you're right that it will run out eventually, and it actually decays exponentially. But we have less power available now, 9 years into Curiosity's mission, than we did at the start. But we still have enough power to run the instruments. The thing is a little bit oversized deliberately for that purpose. And you can learn to be more efficient, and you can slow down a little bit. We don't drive as, maybe eventually on Curiosity, we won't be able to drive and run the laser on the same day, perhaps, right? Or drive and run the robotic arm. But drive on Tuesday, robotic arm on Wednesday. You can still be productive. And in fact, another RTG powered mission, Voyager, was launched in 1977, Voyager 1 and 2. And they're still operating. And they expect to operate those into the mid-2020s. On greatly reduced power budgets. They've turned off most of the instruments, but they're still working more than 40 years later. So
interesting. So we're, of course, here at a museum in Nevada and always looking for interesting gallery exhibits. And actually the gallery I'm sitting in is our changing exhibit gallery, where we often do 2-dimensional imagery. So it's just pictures on the wall. So one of my members says, do I see a future exhibit or gallery display from this mission?
Well, I certainly can't make any promises on behalf of NASA, but I think that would be an interesting exhibit. And there's plenty of gorgeous images like this from Mars and images from Nevada, which we might well put into some kind of display. That seems something that's possible. And if it's something that the museum is interested in, we could talk, and I would involve the JPL media office in how such a thing might be done. But yeah, I think this is an interesting story to tell.
All of the people who've commented agree that it's fascinating and interesting and all of that. So yes.
Okay, well, let's talk about this afterwards, and we'll see what what might be possible.
So I would like to go ahead and thank Raymond very much for doing this today. like I said before, I just love aerospace stuff. And I know it's, it's important to everyone, not just you guys in Pasadena. So thank you for sharing that with everyone.
Yeah, and thank you for inviting me, and thank you to the state of Nevada, and particularly the people of Hawthorne and Mineral County for welcoming us, and also the Hawthorne Depot, run by the Department of Defense, who hosted us on part of their land, just outside the fence. What turned out to be an excellent field site. So thank you very much.
And we also talk about that changing geology of Nevada here at the museum. So how there were, old lake beds and sedimentary deposits and everything. So we can relate our geology to Mars now.
We absolutely can.
Well, thank you very much, Raymond. It's getting to be that time, so I think we'll wrap up.
Okay. Well, great. Well, again, thank you for having me. And I hope people enjoyed it.